don't have a. Yes.
All right. Okay. Hi, everyone. So today we're going to continue our seminar series with Jonah Kudler-Flam from IAS. He'll is visiting us. He'll be around tomorrow, well, today and tomorrow. It was here yesterday. He'll be talking about horizons and eavesdroppers, decoherence from soft radiation. Thanks.
Thank you very much for the invitation. So today I'm going to talk about horizons as eavesdroppers. The figures have not compiled, so I'm going to try to just draw all the figures here, but if those aren't clear, just please interrupt me at any time. Let's see if this works. Okay. So, all right, before I actually go into this, I want to just give a bit of an overview. So the idea is that, throughout physics, energy and entropy are intimately connected through statistical mechanics and even quantum field theory. And frequently, we always consider some change of entropy to always come with some change in entropy, some change in energy. And I'm going to be talking about this interesting gedankenexperiment that was talked about by Wald, Danielson, and Satishchandran. So the work that I'm doing is with two of these authors, where they consider a specific example where decoherence in the experiments comes from with no energy loss. And so this is an interesting kind of playground to work with and think about the relationships between energy and entropy. All right. So let me set up the problem. So consider some experimentalist, Alice, who prepares some spatial superposition. So let's see. So she has a single charged particle and she sends it through a Stern-Gerlach apparatus, and half of the particle or the half of the wave function is maybe a little better.
That's where the decoherence starts.
Okay, so Alice, half of her particle is to the right and half of the particle is to the left. The wave function, that is, the single particle, it has charge Q. And it's separated by some distance that we'll call D. Is this readable?
Okay, sure, getting a different marker. Let's continue.
Okay.
Oh, okay.
Thank you. Oh,
All
my
right,
goodness.
that's good. Thank you. Thanks.
D, and this is Alice.
Actually, writing a little bit further up.
Yeah. Alice, and is that high enough?
Yeah.
Okay. And so she prepares some spatial superposition. And so she has spin up going to the left trajectory and spin down going to the right trajectory. And we give her a finite amount of time to recombine her particle, and she wants to maintain coherence. So let's see, she puts it through some reversing Stern-Gerlach apparatus, and this particle recombines, and she wants to minimize the radiation as to maintain the coherence. So she wants to have some pure state at later times, such that it's the same state that she started with before she separated this trajectory. That was supposed to be a picture. Okay, so now she has an adversary, Eve, who's sitting over here. And Eve wants to destroy the coherence of Alice's superposition. So they're working against each other. But Eve can make measurements of the Coulomb field generated from these two different trajectories. So these will source two different Coulomb fields. And then Eve can measure the strength of the Coulomb field over here. So for example, we could have Eve have her own particle, charged particle in some box, and release that charged particle, and it will react to the Coulomb field in two different ways, depending on the trajectory that it's sampling. So if given enough time, the deflection between the particle can be measured by Eve, and then she can harvest which path information. So the difference between the two deflections will be large enough for her to distinguish which path Alice went on.
Now, presumably she's doing this without messing up the information she's measuring, right?
Yeah, so
I mean, she could measure something and collapse the wave function to the side and the information is useless. She's doing this in a way that preserves whatever she's measuring. Is that the idea?
yeah, what's important is that she's at some distance away such that she can't send any signals when Alice has the superposition open. Say she does some measurement, it shouldn't affect the state here. So yeah, this is so from Alice's perspective, there should be no like Eve. It doesn't matter if there's an Eve doing something or not.
Sorry, here, the key idea distinction from what you're familiar with in quantum mechanics is that here you're using the long range force. That's the basic idea. Something that is universally coupled, for example, gravity or gauge theory.
Yeah, that's pretty central. Is that there's some long range force, and that Eve can now measure and gain information about this, even when she's at some far distance.
So I'm still not sure, why are Alice's particles not being affected by what Eve is like? If these particles observe some deflection of this long range force, like why is that not happening to Alice's particles?
Yeah, so let's consider Alice had this was a very good experimentalist and just very adiabatically separated this wave function at early times and just held it fixed. So minimizing she has essentially zero radiation going at electromagnetic radiation because this acceleration that she did at the beginning was as slow as she possibly wanted it to be. So at this point in time, the state is very coherent. It's this equal superposition. But then she's going to be then she has a certain amount of time to recohere, and if she's not given enough time, then she's going to be forced to radiate some amount of radiation. If she's given forever in time, then she can do this so adiabatically that she doesn't radiate and maintains coherence. And from Eve's perspective, Eve is sitting over here and can just, because the superposition has lasted for a very long time, these Coulomb fields have lasted for a very long time. She can make some measurement, but she's out of causal contact with Alice. And so there's this interplay of how much information can Eve gain about this superposition, while still being consistent with the causality of not actually being able to affect the coherence of the state.
So, but I mean, when the thing split, the information that this happened provides at the speed of light, I assume. So
This splitting, yeah.
Yeah.
So this reaches Alice, this reaches Eve.
So it has enough time to reach me, right?
Yeah, enough time. Yeah, let's think of this as it's been in the superposition since the beginning of time. It's probably the easiest way of thinking about it. Yeah, so she can definitely sense the differences. But for consistency, we want the decoherence due to Alice's radiation to always be greater than the information that Eve gets that could decohere her. So because this is out of causal contact, Eve shouldn't be able to do anything that actually affects how decoherent Alice is. So let's write the global quantum state, including the electromagnetic field. So more precisely, we have the state moving to the left, which is sources one electromagnetic field, and the state moving to the right, which sources this other electromagnetic field. Okay, so even at intermediate times, you could think of what's the state of Alice's particle at intermediate times, say just like right here. What you would do is you would look at the reduced density matrix on Alice by tracing over the states of the electromagnetic field. And because these two states are very different, these two Coulomb fields, their overlap is close to zero. And so the density matrix for Alice would be close to like the maximally mixed state. It's like some 2 by 2 matrix that's, close to 1, 1, 6, 0. But this is not really the decoherence we want to be thinking about. This is what we sometimes call false decoherence, because Alice could have just slowly recombined the particle and gotten back this coherent state. So the coherent state is the density matrix where you have these large off-diagonal components. So instead, we want to be able to separate what's the true decoherence due to the radiation that Alice emits versus the decoherence of just these Coulomb fields that she has the ability to recombine at later times. So in order to separate these two effects, it's useful to go to asymptotically late times. At late times, let me draw a space-time diagram. So we're in flat space. Alice has this superposition, and then at late times recombines the superposition. And so there's radiation that goes off to null infinity, located here. And so that's the true radiation. So we can consider a state at asymptotically late times. And so that state is some state of the radiation that reaches infinity with some state of Alice's particle at future infinity, I plus. And then we'll define decoherence as 1 minus this overlap of the radiation. So if there's no radiation or minimal radiation from these two trajectories, then these states will have overlap about 1, meaning that the system has retained coherence. These off-diagonal elements, the off-diagonal elements are these overlaps, side left, side right at infinity. And this is equal to 1 minus e to the minus number of particles emitted, like number of photons emitted at infinity. So if one whole photon is measurable at infinity, then someone at infinity can distinguish these two states because they've measured a photon, so they know it went one way or the other. So these papers on top try to or do resolve the consistency of making sure that Alice decoheres herself as much or not, if not more than Eve can decohere her by these kinds of calculations. So Alice's experiment, as I've mentioned, is limited by the amount of radiation that she emits to infinity. And the amount of radiation goes as QD over T, where Q is the charge of her particle, D was this distance between the two trajectories, and T is the amount of time we give her to recombine. So if she's given much more time to recombine, then she can minimize the decoherence. And so she can retain coherence if T is much bigger than QD. Meanwhile, we had Eve measuring the deflection of the particle or test particle that she's looking at, that she's using to measure the Coulomb field. And these go across two trajectories. And she's able to distinguish this these two trajectories, if the deflection is bigger than just the vacuum fluctuations. So there's vacuum fluctuations that are related to the charge of her particle over the mass of her particle, and the amount of deflection her particle does based on the two different Coulomb fields is given by this formula, and it works out such that for her to gain information about which path, it has to she has to have a time of releasing this particle that's longer than q times d. So the point being is that these two things are not simultaneously achievable. So, okay, so T is much larger than QD, and QD is much larger than D. Capital D is the distance between Eve and Alice. And so this distance is like equivalent to the amount of time that Eve has to release these particles. And so these two conditions, this one and this one, are not simultaneously achievable, meaning that Alice can decohere herself just as much as Eve can decohere her. So this was an example of something that some eavesdropper Eve could do far away, but you could ask, what if there were many Eves, like doing all sorts of measurements outside, and what if they were doing fancier measurements than just releasing some particle from a box? And everything still has to remain consistent in that, this big collection of Eves needs to be not as powerful as just in terms of discriminating these two paths as the decoherence of Alice herself. So once considering this more general framework, it's very natural to think about this whole setup in terms of quantum aircraft. But are there any questions with just this original setup?
I'm just trying to understand the terminology. So when you say Alice can decohere herself, what exactly do you mean?
Yeah, so I mean, she starts with some state where her density matrix is perfectly coherent. It's 1, 1, 1, 1.
Yeah.
And then she does this recombination.
Yeah.
And by emitting radiation, her state becomes like 1/2, 1, 1, but now psi left, psi right at infinity, psi right, psi left at infinity. So her off-diagonal components become the two different states of the radiation.
So sort of Alice's goal is not to decohere.
Right.
I see.
So she wants to not radiate. Yeah.
Alice will decohere herself as much as Eve can make her state decohere.
Yeah.
I see.
What would be bad is if Alice has not decohered at all, but Eve is able to learn information about Alice's state.
Goes against her correction.
Yeah. Yeah, which was not the original framework of this experiment, but I think everything becomes clearer when we talk in terms of error correction. Okay. So I'll take a detour into quantum channels. So in quantum mechanics, we can do, there are legal maps between density matrices, and these are called quantum channels. And so generally you can think of these as you take some quantum state, you add in some auxiliary state that's fixed, you apply some global unitary to both of them, so you're coupling both of them together, and then you lose some information, you forget about part of the state. I think some of these subscripts are just wrong, so please ignore the subscripts here. So just think about, you take some system, you add in some auxiliary system, you couple them from evolution, and then you forget part of the state. There's a notion of a complementary channel, where instead of forgetting you do the exact same thing, except instead of forgetting that part of the state you did before, you forget about the other part of the state. So if I have in this picture where we started with Alice's particle, so she starts with some state of her particle. She sends some of this state to herself later, and she sends some of this state to Eve over here. And so there's like some global evolution that's unitary, but when we split between Alice and Eve at later times, there's a split in the information in Eve given to Eve and the information given to Alice. So this would be the quantum channel, the thing that sends here to here, and this would be the complementary channel that sends Alice to Eve.
The definition of the complementary channel, not one sigma B to the pure state. Because otherwise it's still not fully uniquely defined.
Sigma B to be
Sigma B, so this definition, you want it to be unique, the complementary channel. So you would want the Stein spring representation to be maximal. Right, so I think you want sigma B to be a pure state to define the unique.
Yeah, I agree. For uniqueness, you need this to be a pure state. Yeah. It need not be a pure state for just the definition of a quantum channel, but yeah, for the uniqueness, yes, yeah.
But I imagine you want to use it for error correction or there.
Yeah, so in this scenario, think of the state that you're adding in as the state of all of the quantum fields that you add in that the particle could couple to that starts in some vacuum state originally, and then you evolve with the vacuum plus the particle. In that sense, it's unique. Okay, so what does it mean to maintain coherence? In this language, Alice has not decohered at all if her channel is perfectly reversible. So if this map from her state to here can be perfectly reversed such that she can gain the state she started with. And so this reversing channel is what we'll call D, the decoding channel. And so if there exists a D such that composed with the channel and it just gives the identity, then there's no decoherence. Of course, there's always some decoherence, no matter how slowly she had done this. There's going to be some radiation, even if it's negligibly small. So we want to have a more general definition that quantifies how far how irreversible this process is. And for this, we consider the diamond norm, which is some fancy norm, but that's appropriate for measuring the distances between quantum channels between this recovered channel from the decoding and the identity. So this is our new definition of decoherence. Remember, the old one was just 1 minus the overlaps of these radiation states. Okay, yeah, clearly this is more like general and maybe just seems overly technical for no reason, but it helps for some reason that's I'll talk about soon, and also just for consistency, you can go through the computations of this norm and whatnot and find that it's actually the exact same. It takes the exact same form for this simple example that I talked about before. It's really just 1 minus the overlap. So now that we've defined what decoherence means for Alice, we want to talk about what does information mean for Eve. So before I was talking about, she can tell the difference between these two paths, and that means she's gained which path information, but let's quantify that. So if Alice can distinguish two quantum states, say these two states of these two paths, using a single quantum measurement, this is equivalent to the trace distance between the two states being large. So the trace distance is this, just the one norm between the two states, so rho minus sigma. And so we'll define the information available to Eve as the maximum trace distance between any two of Alice's initial states. So, for example, the up state was this trajectory and the down state was this trajectory. We'll have some a large trace distance between them. And this means that there's some information that's propagated to Eve. And this maximum is pretty much this, you can think of as just this diamond.
I have a question.
Yes.
Why are you comparing complementary channel to recovery? Is that the recovery part?
Yeah, I was about to say what R is. R is not, so D was our decoding channel.
Okay, yeah.
R is a different channel that takes every state of Alice's initial system to some fixed state. So it like is, say it takes all of these to just some state as if there was no particle there at all.
Okay.
Forgetful map.
Yes.
Forgetful.
Yeah, the forgetful. So yeah, so equivalent of this is the distance between the channel that sends the information to Eve and the channel that contains absolutely no information, which is R. Okay, so it'll be convenient for us to consider not this trace distance, but a related quantity called the fidelity, or Halevo's fidelity. That's defined like this: trace of square root of rho, square root of sigma. And we can think of these as equivalent, trace distance and fidelity, in the sense that they both upper and lower bound each other. So they're giving us the same information. And then the real workhorse is this theorem called the information disturbance tradeoff, or one form of the information disturbance tradeoff, which says that information is both lower and upper bounded by the decoherence. So this is some theorem from these authors, and you can remember from before that these are just our definitions of decoherence in information. Just using these definitions, you can see the following results is that if Alice has not decohered, then Eve cannot have received any information. And so the contrapositive being that if Eve has received information, then Alice must have decohered. Okay, and then the converse also holds because this is bounded from both sides. So if Eve has not received information, Alice has not decohered. So really, and from quantum error correction, nothing is mysterious about this original setup with the Alice and Eve, and whether Eve can decohere as much as Alice. Yeah, so it all follows from just error correction.
I'm
Yes.
confused right here. So you said if Alice goes extremely slowly, almost adiabatically,
Yeah.
spreads them out. So then she, from her perspective, she's not decoherent because there's no radiation loss. She's a closed system. She's not an open system.
Yeah.
So, but from Eve's perspective, far enough along, there are two different Coulomb states. I mean, right? From Eve, so Eve can still pick out which Coulomb state Alice is in.
Yeah, so this was the original problem, but the thing is, if she takes a really long time to do this process,
Right.
then for Eve to be space-like separated from this, Alice's thing, so that she shouldn't be able to influence it, Eve is pushed out really far away. Because, this is taking a really long time to recohere, and so Eve needs to be way out here in order to be space-like separated.
Right. You're saying here, if Alice has not decohered, then Eve cannot have received information.
Yes. Yeah. So it's this trade-off between, how much information Eve can receive and how much Alice has decohered. So these things should really be thought of as equivalent notions.
Got it. Thanks.
Let me ask you another related question. The way to describe decoherence is it's either decoherent or not. It's sort of a binary operator. But what about sort of decoherent or some intermediate state? How is that represented in there?
Oh, great. Yeah. So I've been talking in these absolutes, but this is some number. These are numbers between 0 and 1 or 0 and 2. That 0 means no decoherence, and like absolutely no decoherence, and 1 means full decoherence, meaning these off-diagonal elements would be like 0. But then this is some number that just interpolates between the two, and as you interpolate between the two, the other quantity also has to interpolate between the two. Yeah, so it's this nice continuous thing. Okay, so far, you've noticed there's no horizons in the story, and my title had horizons in it. So now let's consider doing the exact same experiment in the vicinity of a black hole. The question is, now give Alice as much time as she wants. Can she maintain coherence? Remember, in the flat space case, if we gave this amount of the amount of radiation went like inverse squared with the time we gave her to do the recombination event. And so if we had given her, infinite time, she could have completely maintained coherence. But we're going to find something different in the case of black holes. So now the picture is, so I'm going to draw a Penrose diagram for a black hole. So this is the exterior of the black hole where Alice does some experiment. And this is the interior of the black hole. Here's the singularity. And so let me call this H plus, which is the horizon of the black hole. And this is Sprat plus, which is null infinity. So the key is that now Alice, when she moves her particle, she doesn't just radiate out to infinity, but some of the radiation can go through the black hole horizon and at the singularity. So the global state looks like this. It's some superposition of up going to the left, plus the radiation on the horizon in null infinity, and then the complementary trajectory where Alice has gone to the right. Alice's particle has gone to the right. So this is where the quantum information perspective is kind of useful, because even if we give Alice an incredibly long amount of time to do a recombination, which did save her in the flat space case, she's going to have to decohere because Eve can now sit behind the horizon and is not able to causally influence her. However, she can make measurements behind the horizon and distinguish these two paths.
Did you mean Paul?
Yes. Yeah. Did I mean Paul? Maybe she has a rocket ship in there. But she'll eventually hit the singularity.
Will not go.
For a little while, maybe. Yeah. She will hit the singularity. Thank you. Yeah, so okay. But there are different Coulomb fields inside of the black hole that now Eve can distinguish these two paths, even if Alice had all the time in the world to recombine. So this horizon is playing a new, has a new effect. And by this information disturbance trade-off, because Eve is able to gain some information, we know that Alice must have decohered to some extent.
That's right, but Eve has finite time now.
Yes.
So it's true that she has access to H plus info, but she has finite amount of time. Before she had like a lot of time, right?
Right. Yeah.
And that doesn't affect the.
Okay. Yeah. So I'll back up this intuition, which was like hand wavy with some explicit computation that shows to what extent Eve can gain this information.
But is the idea that even if Alice has infinite time,
Yeah.
there is a, I guess, upper bound on how much she can keep coherence.
Right. Or sorry, a lower bound, or depending. Okay. Yeah. Upper
How
bound.
much she can error correct.
Yeah. Yeah. Exactly.
She cannot do perfect error.
Yeah. And what's important is that this is some finite proper distance away, so the Coulomb fields really look different. All the way in the flat space case, if like Eve is pushed to infinity, Coulomb fields don't look different at infinity, these have fallen off. But this is some finite distance away, so there's some amount of measurement that can be done. Okay, so as shown by these authors, the mechanism for this decoherence is the presence of soft radiation that must go through the horizon. So by soft radiation, I mean photons that have arbitrarily low energy that are propagating through the horizon. So because Alice can do this adiabatically, she can minimize the amount of energy flux through the horizon. But what they show is that you can't minimize the amount of photon flux. So there's going to be some number of photons. So they compute just the overlap of the two states, two coherent states sourced by these Coulomb fields on the horizon. And for these two particles or two trajectories, and this will decay with, so it's, remember, it's e to the minus number of particles that go through the horizon, and the number of particles they show grows linearly with the time that Alice does this recombination event, or Alice holds this superposition. So, you know, even if Alice goes extremely slowly, you know, this time actually is giving Eve more of an ability to distinguish the two states. Okay, so let's see.
But this is not related to thermal flux of working photons or any such stuff, because now Alice is in the thermal band of thought.
Yeah, so good. You could also worry that there's decoherence due to Hawking particles, but it's shown that this is a distinct effect, one, and that it can also be arbitrarily weaker than this effect.
Very much. Yeah.
Yeah, this is like,
You can take a very large black hole. So you can take a very, very large black hole, which doesn't radiate, let's say, arbitrarily large black hole. And so then the Hawking radiation is infinitely weaker. Is that how you argue this?
Yeah, so you can actually just so what they do is they explicitly calculate like the decoherence due to the interaction with Hawking quanta, and just the decoherence rate has just a completely different form. It falls off much quicker with for example distance from the black hole.
and this origin can go to zero and nothing changes, right? Because there's no back reaction.
Yeah, we're not treating back reaction. Yeah.
So it's parametrically different from Hawking.
Oh, there is G Newton in here. I can try to find. An equation will come up soon. That's the number of photons in time, and it depends on like G times M, like the mass of the black hole.
Because looking at a big black hole naively will not necessarily help, because there must be a dimensional quantity in front of T in the exponent. And the only thing that occurs is the radius divided by radius of the horizon, the divided by Schwarzschild radius. And then making it big will mean that it will have very long time to wait before something is happening. I mean, I'm making this up, but it's not obvious that times and distances work out, but I'm not saying I know that.
The thing is that, I mean, when you have infrared divergence, it's needing a number of photons, but the total energy is fine. We have some agreement to say that we look only at total energy and not number of photons.
Yeah.
Because that's not physical.
Yeah. So here, you can make the number of photons, finite, but keep the energy as small as you want.
That's what Martin is saying.
Yeah, and I mean, I would say that two states that have like one has an infinite divergence and one that does not, these are distinguishable states.
But in quantum electrodynamics, sometimes we say that no, that if we do things cleverly, then infinite divergence will disappear. Then is that what?
Yeah.
You should look at the rest. It's not physical, that it's because you're looking at particles that are not properly addressed
Mhm.
by the Coulomb fields that you would take.
I don't remember.
All the details anymore, but right. So indeed, in this case, when energy can be made very small, but the number remains finite in standard QGS system. I'm not saying it's the same here. But,
Yeah, okay, so, yeah, this next thing that I will say, yeah, please complain if there's something, yeah, with this, because this is directly, what you're pointing out, yeah, so. So let's consider first, just a stationary particle outside of a black hole. And so the electric field on the horizon is purely radial. And the radiation, or what we're calling the radiation, is the pullback of the electromagnetic field to the horizon. And so E is the electric field, and A is the vector potential. V is the affine parameter on the horizon, this null parameter, and the subscript A is angular coordinates of like the two sphere on the horizon. And so the affine component of Maxwell's equation on the horizon is just the angular derivative of the electric field of the radiation is equal to the derivative with respect to the affine parameter of the radial component of the electric field. And so no matter how a particle is moved, so if you do it even very slowly, if you integrate this equation along V, there's going to be a change in the radial component due to this dipole moment between these two trajectories, and that change will be related to the radiation, this EA on the horizon. And so no matter how slowly you do this, you're forced to have some finite amount of radiation. Yeah.
I'm thinking about something basic. So if the observer is just hovering outside the horizon, they're definitely accelerated,
Yes.
right? And that means that they're radiating photons no matter what, right?
So if they're following this killing trajectory, so here I'm having them following just some time-like killing trajectory outside the black hole, and in this case, they're actually, even though they are accelerating, they're not like in free fall, they are not actually going to be radiating. So like this source like has the symmetry of the space-time.
Yeah.
And so the Coulomb field is static. Static, yeah. And whenever that gets confusing for me, I always go to the case if this is in de Sitter space in the static patch. When you're actually static, you get the same effect. So there's it's even easier to think about.
Because this, what you're discussing is just a property of the horizon, it has nothing to do with black hole versus cosmological horizons.
Right. Everything said is a statement about horizons. Yeah. Yeah. Okay, so this is supposed to be a picture that I'll draw here. So, so we have like the vector potential as a function of the affine coordinate, and when this particle is moved and displaced forever, there's going to be some delta A. Remember, this is not, I'm moving it and I'm not returning it to its initial position. So the quantum state on the horizon is some coherent state. So we take the vacuum and then we apply some unitary operator, some coherent operator. And the expected number of particles is given by the inner product in this one particle Hilbert space, which goes like the omega, and then A squared. So omega is the Fourier transform of V, which was the affine coordinate on the horizon. And A hat is the Fourier transform of the vector potential. And then this is just an integral over the angular coordinates.
Sorry, the state we're discussing is the under state.
Yeah, good. So, for technical simplicity, you go to the Hartle-Hawking state, the Hartle-Hawking vacuum, and you compute this in. But the Hartle-Hawking vacuum and the unroot state are the same at low frequencies, where all of these calculations are being done.
But view this calculation with two-sided black hole calculation.
Yes, yeah. Yeah, you could view it in either way, because at low frequencies, they look the same. At higher frequencies, unroot and Hartle-Hawking look very different. But at low frequencies, this is the same. Yeah, and these equations are for Hartle-Hawking vacuum.
I have another question.
Yeah.
The way you describe information, it's like an independent quantity living by itself. Suppose you're looking at a gas or stream of electrons. An observer can either be measuring the total number of charges to get some information, and his husband can be measuring the atom, can be measuring the total mass energy or whatever. It's implicit in what you're saying, if I understand it correctly, that the information is inherently its own quantity, irrespective of how it's measured. Am I understanding that correctly?
Yeah, so this is why I wanted to move from the perspective of thinking about like an explicit Eve who's releasing particles and doing some explicit measurement versus just what's the information content in the state. So what these quantities like this trace distance actually explicitly means is consider every possible measurement you could ever think of. That's legal with quantum mechanics. So this is Adam and Eve and all of their friends making measurements. And what is the very best thing that all of them could do? And so this is telling you it's actually like a maximization over what's the very best measurement all of them could do. So it's characterizing the best measurement.
So it's implicit that information in and of itself, irrespective of how it's obtained, so to speak, is the quantity of relevance, irrespective of how you've done it. So is that right?
Exactly, because and without these kinds of optimizations, we don't have the power of this information disturbance trade-off that relates the decoherence to the information. So this is what I'd like to think is more like absolute thing.
Sorry, I think that was the error correction part of the story that you described before was precisely what we were just discussing. Right? It's just about information.
Yeah.
But here you're talking about a dynamical setup where there's a Hamiltonian and there's a clock that's ticking, and it's important. Right?
Yeah, that's kind of what's in the background.
The second example is, well, maybe we'll come back to this later. But the existence of a horizon,
Yeah.
you specify something more than just information disturbance inequality. There's some sort of more dynamical input to it.
Yeah, information disturbance is kind of like the kinematics, and then this is a specific this horizon scenario is like some specific quantum channel one can consider that that we can apply information disturbance to understand it.
With sort of a quantum channel that will not preserve. You cannot error correct. Okay?
Yeah. This is saying we're interested in this quantum channel of Alice doing some experiment outside of horizon. Let's apply the techniques that quantum error correction people have, the theorems that they have used.
A sequence of quantum channels associated with time.
Yes.
And none of them. So previously you had a sequence of quantum channels with the limit of t going to infinity, you could do good quantum error correction. Here in this case, no, for all t, even if it's close to infinity, none of these guys can do arbitrarily good error correction.
Yeah, so what we can do, because you could say the quantum, the channel up into a certain time, just the map from this state up into Alice's, lab at some time. And you could ask, as a function of time, what is the coherence of her experiment without her ever having to do some measurement? So, and then how is this related to the amount of information that the black hole has received up until that time? Yeah, so it's a more local way of thinking about this. Also, I think this clock is broken, so can you maybe tell me when I'm like running out of time?
Okay, sure. Yeah.
I think I have time now, but yeah. So just for this example, at low frequencies, this looks like some step function, which will go like 1 over omega at low frequencies. And so this is so 1 over omega squared, and then so you can see that this is logarithmically divergent if we never close this A. If we never close the superposition. And so this is the infrared divergences previously brought up. And this is saying that there's some infinite number of photons radiate at the horizon, but they're very low energy. If the particle is displaced at a later time, this will be some infrared cutoff, and this is the computation where that the number of photons actually grows linearly with time. So this amount of this is like affine time is roughly like e to the sum over t, where t is the proper time of Alice, and then it's logarithmically divergent. So we take some like logarithm of this, and that will be linear for t. And so this will imply that Alice decoheres in some finite time. Okay. So now we want to use all of this error correction stuff to make this more precise. So we want to compute the quantum fidelity as a function of time. So why quantum fidelity? Well, this is a natural generalization of this overlaps that we've been computing. So instead of going to this infinite time regime where these diagonal elements are overlaps, we now want the generalization of overlaps to mixed states, and the generalization of overlap to mixed states is the quantum fidelity. Okay, usually audiences aren't as familiar as this audience with Tomoe Takasaki theory, but I'm not going to assume it. So to compute quantum fidelity in quantum field theory, we use Tomoe Takasaki theory, which is, I'll just introduce the first, the ingredients. If we have two states that we want to compute the fidelity for, and we want to compute the fidelity with respect to some algebra, which means we only have access to the quantum state, say, before some certain time V0. So this is some mixed state. So we have some algebra associated to this region. So this relative Tomita operator takes some element of the algebra acting on one of the states to the dagger on the other state. And then you can do a polar decomposition of this operator to get some anti-unitary piece and some Hermitian positive definite piece. And the fidelity is then just defined as the expectation value of this thing in the quantum state.
We want to compute the fidelity for two states of the horizon algebra?
Yeah.
And that's type 3-1, that's why you're 1 3 1.
Yeah, so there's, okay, yeah, it's type 3-1, so that's why we're doing modular theory, but also I actually don't even know how to compute these things without modular theory, so this is one of those few times that I can do the computation more easily using the fancier techniques.
Okay.
Yeah. But yeah, to do everything precisely, I mean, I know I've been talking about density matrices for a while, but to do everything more mathematically precisely, we don't want to talk about density matrices. But I think it's safe to just still have density matrices in your mind, and this is just, you can consider this a computational technique.
That's another question. So
Yeah.
now you're talking about the horizon, right? But previously you said that, oh, there could be several Eves, right? So I can think of an Eve that's like capturing stuff on the horizon and another guy who captures stuff at infinity, right?
Yeah, so let me make this better. So this is V0, and then maybe I shouldn't have drawn the other side of the black hole. Let's then up until this point, this interior of the black hole, this is the region that Eve is living in.
And the two states, one of them is the vacuum from from the thermal field level.
Mhm.
And the other one is a coherent operator acting on that, so it's a coherent state.
Yes.
But isn't that, in that case, isn't fidelity just, is a unit of rotations? Yeah, we'll discuss it later.
Sure, yeah. So this is some mixed states up to this point. So we want to know how much information Eve has when she has part of the interior before she's hit the singularity. And then as this increases with as we increase this cut. And this should be related, by propagating this. It should be related to the amount of decoherence that Alice has had up until some certain time by information disturbance. So technically, we just want to compute this. Here are some facts that we need, but you can ignore them. These are just the standard facts from Tony. Let me also okay. So one of the few times that we can actually compute these relative modular operators, it's felt very abstract, but one of the few times that we can actually compute it is when you have coherent states over a vacuum state. And in this case, this operator we're interested in is related to this operator that instead of taking one state to the other, it takes the vacuum state to itself, but now it's just conjugated by these unitary operators. So conjugated by these operators creating the coherent state. I've mostly written out derivations explicitly because just to emphasize that everything in this derivation is actually quite straightforward. It just is follows from standard properties. So, but using this equation, the fidelity is just given as the expectation value of this modular operator in some excited state that's created by these coherent operators UI.
It is a segment of the orientation writer.
Yeah. So yeah, it's sorry. That should be labeled by V naught. It's like we have A is this side and A prime is this side. So if Eve only has access to A, the fidelity on the amount of information she has should only be dependent on the state here. It shouldn't be dependent on the state to her future that she has no information.
Should not A prime include the infinity out of infinity? Shouldn't
Here?
Yeah. So that is the whole thing is B of H?
Yeah, so this part is for both states is just tensors with the vacuum at which is essentially the vacuum at
Yeah, well, the idea that is that you think that A prime is B of H.
Yeah,
Type one.
The total Hilbert space is you have the Hilbert space of H plus tensor product the Hilbert space of Stride plus. Yeah, so from the argument earlier in the talk that you can minimize the radiation going out to infinity, the same thing holds in the black hole space time. Then you can minimize the radiation going out to actual null infinity, but you can't minimize the radiation going through this finite horizon. Yeah, and we'll just assume for now that the fidelity associated to this state at infinity is it doesn't contribute anything because both states look exactly the same.
Oh, because you have in mind the under vacuum. Because if I'm taking the we'll discuss it. But I'm just thinking.
And let me just redraw this picture. If Alice has recombined at some finite time, but that's before the time accessible to Eve, these two curves look exactly the same, so Eve doesn't know, she can't tell the difference between the state that has this infrared divergence and the state that doesn't. It's a side comment. You only can tell the difference between these states once she can sample this region where there's this recombination. That's what I'm saying here, and the picture is supposed to be that picture. Okay, and I didn't finish the argument for why we can actually compute this, because I had left everything in terms of this, abstract modular operator. But essentially, the one time we know how to compute the modular operator is for the vacuum state, and its generalizations, like for this Hartle-Hawking state. And in this case, the operator, this modular operator is just the boost operator, K, or e to the boost operator. And this J, the anti-unitary part of the Foley decomposition, is just the CRT conjugators, where R is just flipping space. This was the thing we wanted to compute the overlap with the vacuum. And I'm just saying here that it's equal to computing the overlap of U, and where U is the coherence operator and the operator that's conjugated by J on the vacuum. Yeah, so we want to compute the overlap between the vacuum state and this kind of CPT conjugated state. Exactly, yeah. So let me draw what this state looks like. Say this is V naught, and we have some, lump here. Then the CPT conjugate is going to get some lump that's been reflected over this V naught portion. And so we'd be taking so this is what the UJ, and then we want to take the overlap of this state with the vacuum state. Oh, I have the picture there, great. That's the first picture that's shown up. Right. And so with this, the fidelity as a function of time is straightforward to compute. You get a piece again that's like e to the minus number of particles in now this larger state, this kind of mirrored state. And then you get this extra contribution that decays with time that is really that is telling you how your measurement gets better as you are given more space. If you're able to take larger amount of space, then you can take you can make measurements of lower frequency radiation. You can do fancier kinds of measurements if you're allowed to fit more Eves into the black hole. So it decomposes into these two pieces. This formula S is just the profile of this thing. But as you take V naught to infinity, you recover this the equation from earlier, which was just the overlaps between these states. Okay. Is there a question? Okay, so as mentioned before, everything holds in de Sitter space. So let me draw de Sitter space, no black holes. De Sitter space has a horizon, it's the cosmological horizon. And you could have, so we have positive cosmological constant, and we have Alice doing some experiment inside one of the static patches. And all the things I said completely go through. Now Eve sits behind the cosmological horizon. I think I have some equations for the number of particles as a function of time. Fortunately, these didn't show up before, but for the electromagnetic case that I've been talking about, the number of photons grows in time. but it's like inversely proportional to like the Hubble radius. And one thing I have not emphasized so far is that everything goes through if you, instead of considering a superposition of charged particles, you instead consider a superposition of massive particles. And in this case, so you do some, you take a massive particle and you put it in some spatial superposition, and this sources two different gravitational fields. And then you can use just linearized quantum gravity to look at the number of number of gravitons that propagate through the black hole horizon. And this has some different scaling with the parameters, but it also grows linearly with time. What time is it?
5 more minutes.
Okay, so now I just have like a few speculations. But let me stop for a moment for if there's any questions with what I've said. So I have 3 speculations, and I'm trying to think which I should talk about. Okay, yeah, let me talk about something that people have been referring to as the central dogma of black holes. So you might be surprised from just a quantum field theory and curved spacetime. I was surprised that, you know, we're considering like vacuum solutions, and we're considering like super low frequency radiation that's causing decoherence. And this radiation has like wavelength that's like much longer than just the inverse, than the size of the black hole. So it feels like this kind of radiation should not be actually absorbed from the black hole. But let's see. So the central dogma of black holes asserts that as seen from the outside of a black holes act like normal quantum systems, but that are in some like high energy excited state. That just has this quantum system has e to the black hole entropy degrees of freedom. So you can just think of it as some like highly excited metal floating in space as seen from the outside that's interacting with some outside quantum system. And so this is the central dogma. So this experiment, I think, is consistent with this idea that we're in the highly excited region of some black hole and not just this like vacuum solution where you wouldn't assume to, you wouldn't expect to absorb any low frequency radiation. So if I just show you what like the spectrum of some, you know, quantum system looks like, say I take energy like this, and the levels, you know, around the ground state, you might have very large gaps where the gaps are like order the size, the characteristic length of the system, the inverse, and you wouldn't expect to have, you know, absorb low frequency radiation such that, because it wouldn't have enough energy to like excite you through here. But up in the higher part of the spectrum, we have, in the highly excited pieces, we have energy gaps that are like e to the minus black hole entropy, so, or the entropy of the quantum system. And here it's not as confusing to think about absorptions of very low energy states that lead to transitions between these high energy states. So in some sense, this is consistent with this idea that black holes could be thought of as these highly excited quantum systems. So I've been talking about flat space, but really the same story goes through if you're just considering a Schwarzschild black hole in anti-de Sitter spacetime where we understand quantum gravity better. So everything I've been talking about has been like quantum field theory and curved space limit. But it might be interesting to reinterpret all of this in conformal field theory variables where we have a better picture of what quantum gravity actually looks like, including quantum gravitational effects, and maybe probe the discreteness of the spectrum or other interesting quantum gravitational effects. Yeah, let me end there with just that one speculation. Thank you.
Any questions?
I have a question. I think I missed, well, what happened to the fidelity? What's the result for me?
Yeah, so we get just the explicit result is, okay, so it's a little bit, messy.
Okay.
But, unfortunately, so this is like the piece that you get from the pure state, just the overlaps, the number of particles in such a state.
Mhm.
And then you also get a piece that is due to, well, this is a very good marker. So, you know, we've cut off Eve's available region at V naught, and so you can make, you know, bigger and bigger measurements as V naught is increased, and it's so this is characterizing basically how confident is she that she's like that nothing else is going on up here.
Okay.
So it factorizes into these two things.
Okay, thank you. And also, can you go back to the slide of the, where you get the excited states, like UJ? Yeah, that one, this one, the more, yeah.
So yeah, so here I'm just showing that this thing, the thing that I said is equal to the fidelity, it's equivalent to this just modular conjugated U, and using just simple identities like J squared equals 1, and that we can invert the modular operator, and very just simple properties.
Yeah, I was naively expecting to get delta to quarter, to the power of quarter, but.
Yeah, the fidelity is delta to the quarter.
Yeah,
This, you know, squared,
right.
U squared, so we get delta 1/2 when we just take, because we're
Oh,
overlapping,
I see, okay, yeah.
we're overlapping that with just omega.
This is the whole fidelity.
Yes,
This is the
yeah, this is Holebos fidelity. Yeah.
Yeah, which is the overlap in the natural code.
So, do you have so this is excited state, okay, I see, do you,
Just excited by you.
excited by you, can you make state something that is in the other positive ones with the power, ranging from 0 to 1?
Oh, yeah,
And
yeah,
then
so
can you make some physical,
like alpha.
yeah, can you make some physical inclusion of this?
Yeah, so I think so. These are like other like pets like fidelities.
Yeah, so in this case, you can't take this kind of null. You need to find another pair in different positive form. But you can still make the same inner product by using the fidelity.
Right. So let me.
I think you can take this one, it becomes Pets divergence as opposed to what you were thinking of the sandwich.
Does it become this?
Yeah, these are pets divergences. Yeah.
So we
Yeah.
can take LP, non-negative LP spaces, the two norm, the P norm of it, it becomes a sandwich. Sandwich is the right. thing to do,
Sandwich,
right?
yeah. Okay.
That doesn't matter.
But it doesn't give you the fidelity that you want to calculate in that case, right?
This is a special case, very special case.
Yeah.
Yeah, for alpha 1/4, then it will offer a lower. I don't know
Yeah.
if this can be generalized to different
Yeah.
values of alpha.
But this also has another name, Wigner, you wanna say something, WY, it's a spin quantity.
This is just as good for the.
Yeah.
I've seen it called just a million things, and I have no idea what
At
it's
the
called.
time, we're using this back in the 70s. It's just.
Or like a label.
Olivo as well, but
Yeah.
not Alan Cole.
Okay.
Any other questions? I do have another question, so, as you were speculating about what happens in ADS-CFT and the discreteness of the spectrum. So, that, just naively, I would think that based on the intuition you were giving, that there are these gaps -1 order n squared. So at some point, if the observer outside, so if you give the Alice very, very long time.
Yeah.
Right, then she will be able to keep coherence or do better. I would imagine, but now the question is, what is that time scale? Is it scrambling time scale? Is it exponential long time scales?
Yeah, so,
Exponential long is definitely enough. Supposedly, that's the worst.
right, so the timescales needed for decoherence are like So they're much longer than, the size of the black hole,
Sure.
which is why, you know, this ground state kind of picture doesn't, hold up. But, the frequencies are much larger than e to the minus black hole. So I think you would need to probably go to like more of like timescales like e to the s.
Oh, wow, so exponential, classical Poincare recurrences,
I think so, yeah, in order to not see this.
not even scrambling or.
I think scrambling time stuff, you would get this decoherence, yeah.
Oh, wow, okay.
Because then, yeah, because I think my intuition, it's rough, is that you need to go to, you know, you would need to go to timescales where the frequency of the radiation is too too small to like lead to transition.
So your intuition is that you have to be able to distinguish microstates so that this calculation breaks down.
Yeah, I think it holds. I mean, this is totally speculative because you know, we haven't formulated this in CFT, but maybe something could be said, or understanding how, like, where does, you know, this kind of QFT and curve space analysis break down. Yeah.
Any last questions? Not, was, thanks, Jonah, again.